Hello, my name is Terrelonge, and this is my counting circuit. Here are the parts required. Pause the video if you would like to copy the circuit. I'll be explaining this in stages. The first stage is part A. This is the button input. Here there is a pull-up resistor. This means that the voltage is only delivered to the output when the button is not pressed. This impacts stage B by changing the input of the NAND gate oscillator by affecting the first NAND gate. When the button isn't pressed, the NAND gate will output a 0 due to the two 1 inputs it is receiving. When the button is pressed, the NAND gate will receive at least one 0 input, meaning it will output a 1. This 1 then charges the capacitor almost instantly since there is no resistance. When the button is let go, the diode blocks the flow of electricity and makes the capacitor discharge the 1 million ohm resistor in the second NAND gate. The resistor means the capacitor will stay on for a long period of time and hold its charge. The second NAND gate will output a 1 first because its second input is a 0. Or nothing. The 1 of the second NAND gate then goes into the third NAND gate. Since both inputs are 1, the output is 0. Then that output will combine with the output of the second capacitor and output a 1, which won't turn on the LED. This changes when the output of the first NAND gate goes back into its input. Since there are two 1s presented, it will output a 0. This 0 is then carried over to the third NAND gate, which will output a 1 due to the two 0 inputs. Then this 1 will combine with the other 1 still charged in the second capacitor, and the fourth NAND gate will output a 0, presenting ground to the LED turning it on. This cycle repeats forever until the capacitor loses charge. This effect is called a square wave. The next stage, stage C, is a decade counter, where we only utilize one function from this logic chip, the 4017. This chip will read the frequency or rate of the square waves and output a signal accordingly. It outputs a signal to the pin Q0 through Q9 in that order. When it reaches Q9, it resets the cycle. Because we use a 103 capacitor for the second capacitor, the frequency of the square waves would be too quick for humans to observe. The best part about the 4017 is its 12th pin. This pin only outputs a signal once every cycle, or a tenth of the frequency of the square wave. This is where the 4510 logic IC comes in the next stage. Stage D, the decibel counting binary up and down, utilizes the 4510 to decode the square wave inputs from the 4017 and count them. The 4017 output will be fed to the pin 15 of the 4510. Here the square waves are counted and then decoded. The way they are decoded is with Q1, Q2, Q4, and Q8. These are the outputs of the 4510, and each represent the respective digit and a value. The four outputs work in unison to output a number. I'll show you an example of how this works. Here is a breadboard with 4 labeled LEDs. They are labeled 1, 2, 3, 1, 2, 4, and 8, just like the outputs. As you can guess, the outputs and the LEDs correspond to the same number. Now to count these numbers, you have to add up all the lit LEDs together. Here, 4, 2, and 1 are lit. So 4 plus 2 plus 1 is 7. With the 4510, this will work up to 9, with 9 being displayed with a 1 and an 8. This leads to the next stage, stage E, with the binary counting decimal decoder, or the 4511. When you wire the outputs of the 4510 to the corresponding inputs of the 4511, the 4511 will decode this counting and turn it into A, B, C, D, E, F, and G. These letters tie directly into the 7-segment display as shown here. When the 4511 decodes the numbers into the 7 letters, it will then send these signals to the 7-segment display, which will represent Arabic numbers. This is how this circuit makes square waves, then counts these square waves and presents them to humans in an easily consumable way.